What's an exponential function? Why do I think it's sneaky? And why do I think that's dangerous? So an exponential function is usually represented in the form y equals some base raised to the x power. So exponential functions describe exponential growth, and exponential growth is when we count something and over time we notice that it follows a function like that. So how do we know when a function is exponential? How do we know when the growth of some phenomenon is exponential? Well, we know it's exponential when we can notice that after some set period of time, there is a set multiplier that you can apply to the amount, to how the amount changes over that period of time. So for example, often people talk about the doubling time. So any exponential function, no matter what it is going to have a doubling time that you can find. And it's I chose this exponential function because it's simple to see the doubling time in this function. For example, at time 0 here, well, let's talk about this horizontal axis here as time. So that 0 would be some arbitrary 0 time, and let's say that these numbers here represent weeks. So 1 would be 1 week after 0 time, and 2 would be 2 weeks after 0 time. So at 0 time here, we have one of whatever it is we're counting. Let's say that is infected people. So one infected person at time 0. And if we look ahead, or if we allow a week to pass and then we count again, then we see there are 2 infected people. So we notice that after that week, the number of cases has doubled, and we just make a note of that. Over 1 week, the cases have doubled. So now, if we wanted to know, is this growing exponentially, then we would have to wait another week and then compare to see if the cases have doubled again. They have to be doubling over the same period of time, repeating as time goes on. So we look another week into the future, another week passes. At week 2, we notice that it's doubled again. It's gone from 2 to 4 now. It went from 1 to 2, then it went from 2 to 4. So once we've identified that it doubles over some set period of time and it keeps doubling, then we know this is exponential growth. You can also look backwards. In the case of this function, which goes back before 0, we can actually look backwards to verify that this is an exponential function. So instead of doubling, you're going to go back a week, and you should notice that it's a half of what it was. So from 0 time to -1, so 1 week before, it's actually half a case. And then a week before that, it would be a quarter, and then a week before that, an eighth, and then a week before that, a 16th, and so on, until it just kind of just keeps getting closer and closer to nothing. Okay, so now, why do I say the exponential function is sneaky? Well, let's compare the exponential function to a linear function here, y equals 10z. The way to describe in English what this means, y equals 10z, is if z is this time passing again, then every time z goes up by 1, that's 1 week passing. And y equals 10z tells us that when 1 week passes, we get 10 more of whatever it is that we're counting. So here's what happens when 1 week passes. We go up 10. I'm sorry. Yeah, that's 10. 1 week has passed. Okay. So when 1 week has passed in the exponential function here, we only have 2. We went from 1 to 2. And we went from 0 to 10 with this linear function over that 1 week. There it is. So you tell how fast something is growing when you look at its function by looking at the slope. How steep the slope is tells us how fast it's growing. So if you look at this linear function, and we're used to a lot of things that exhibit linear relationships. So we're used to seeing lines on graphs, and this line looks really steep. It is really steep here. It's growing by 10 whatevers, 10 cases per week. And so immediately it kind of shouts at us, hey, this is going really fast. It's changing really fast. Meanwhile, the exponential function over here is not changing in a way that's apparently fast. The slope, the steepness of this curve is very shallow for a good amount of time over here. Meanwhile, the linear function is screaming at us that this is going really fast. So I'm saying screaming because I'm working some emotion into my interpretation of this graph. Looking at the linear function, I think it screams to us that something is wrong. These cases of whatever it is, if they're bad and we're counting them, we're keeping track of them, then they're increasing very rapidly, and that could be frightening to us if whatever we're counting is something that we should be really worried about. And so it's alerting us to the fact that we should be worried about it. Meanwhile, this graph, just looking at it, doesn't really cause us that much alarm, because if we look from the first week, we go from 1 to 2, and that doesn't seem like a big deal. And then even the next week, we only go from 2 to 4. So there's a total of only 4 cases after these 2 weeks, whereas there's going to be 20 cases after 2 weeks for the other function. It's just looks like that's going much faster, and it really is going much faster at this point. So by looking at these graphs, the average person, the person that's looking to see the steepness of this graph, telling them, how much they should pay attention to this situation, they're getting alerted in the linear case, but maybe they're not getting alerted in the exponential case. However, if they apply some understanding of exponential functions, then even when the graph is really low here, they might look and say, well, over here we had a quarter or whatever it is. And obviously you can't have a quarter case of an infection, but let's say you're measuring something that you can go down this low on. Then you say, going from a quarter to a half, that's doubled. That's not so bad. I mean, that would just happen in a week. But then when we notice that it doubles again in another week, now, if we're familiar with exponential growth, now we know what's coming. People familiar with exponential growth know what this means. What does this mean? Okay, so I said that you could tell how fast a function is changing by the steepness. So if we look at this situation, this function that's really steep, this linear function, if we continue to look by scrolling up at these two functions, this one is taking longer to get to be this steep. But if I keep dragging up, you can see that eventually what I've got is a situation where both of these functions are equally steep. So we've actually got a similar steepness. These lines are parallel. And if I keep going, then you start to see that the steepness of the linear function is not changing at all. It's staying the same steepness. Meanwhile, somehow the exponential function is becoming more and more vertical. It's becoming unbelievably steep. In fact, it's almost like it's hard to imagine how steep this is, because it's almost a vertical line. And then at some point, this exponential function actually crosses the linear function and continues growing in a way that is shocking. And if you zoom out, you can see that even though this linear function is kind of steadily growing, over here, after 130 weeks, we see 1,300 cases, or 1,300, that we don't have to wait 120 weeks to get up that high. Over here, after 10 weeks, we're seeing that same amount, and it's almost vertical. So as it changes, it's changing so rapidly that this graph can't even handle displaying it. So it's this feature of exponential functions that they start out in a way that doesn't look alarming. It doesn't jump out at us when we look at the graph, unless we have some familiarity with exponential growth. When we notice that it's got the properties of an exponential function, that's the warning to us that there's something that is going wrong, that there's something that we need to pay attention to, even though we don't see that steepness in this graph. And that's what I think you should know about exponential growth for situations where they might apply.